Hello, everyone. Thank you all for joining us for today's webinar, Practical Business Applications for IoT, Machine Learning, and Data Science. We're so glad you all could join us. Before we begin, just a couple quick housekeeping items. The audience will be on mute, so if you have any questions during the course of the webinar, please be sure to type them into the questions box to your right, and we'll get those answered at the end of the presentation as time allows. And we're also recording the webinar today, so you will be receiving the webinar recording after the presentation today as well. So now, without further ado, it's my pleasure to hand it off to our presenter today, Richard Adams. Richard, you can take it away.
Ashley, thank you so much. Good morning, good afternoon to you, wherever you are today. Thank you so much for electing to spend the next 15 minutes or so with us on this topic of practical applications of IoT, machine learning, and data science. So let's start with the Internet of Things in this agenda. What we're going to do today is just level set and run through some definitions so we're on the same page about what is the Internet of Things. What is data science? What can I tell you about machine learning? But then get very practical as fast as possible. And I want to outline some of the reasons why I think you should be considering an IoT strategy in your organization. So why should you be doing this? I'm going to outline some of the business examples and use cases that I've been working on over the last 18 months or 2 years. Talk to you a little bit about the Hitachi methodology to make sure that you drive value out of IoT very quickly, and then some case studies at the end, making sure that we leave 10 minutes or so at the end for some Q&A. So without any further ado, let's start with the Internet of Things. Over the past 4 or 5 years, the IoT environment and strategy has become a hot topic, and it's not only in tech circles like we are in, but also for the news reading or watching public in general. This whole advent of connected TVs and doorbells and lights and appliances and other consumer electronics has ushered in an era of seemingly smart everything. And sometimes I look around and figure that the things around me are much smarter than I am at some point. But the reality, though, is for business, the IoT industry is really in its infancy. It's only just starting to have any significant impact on the organization and the workplace. So I think it's worth us just taking a step back and considering what is the Internet of Things and what is it not? Well, the first thing that it isn't really is a technology revolution. The capabilities of getting data, which essentially is the whole IoT strategy, is to move data from things that previously were dumb and now they're smart, and get that data into a system where I can analyze and process and gain new insights. Really, this technology has been around for quite a while, especially on the manufacturing floor with OT, operational technology. But what it is, it's a business revolution enabled by new technology. And the reason I say that is really because of the cost barrier has come down so much over the past 4 or 5 years with the advent of the cloud. And most IoT strategies are focused on cloud enablement and being able to take advantage of modern infrastructure platforms and be able to leverage the cost savings that you can see by moving stuff off premises and into the cloud. Now, another concept that you may or may not heard of here is what we call the intelligent edge. And that edge is where all these things that you can see represented in the diagram, like vehicles and electronic robots and CPUs and drones and anything else you can think of that has some kind of chip in it, can be connected together and then to some local processing for things like data monitoring, looking at the health of a machine over time, being able to respond to alerts in real time, maybe for safety or for emergency events. But then ultimately the data itself is moved up into the cloud, into permanent storage, and then a whole host of other services are available to be able to analyze and visualize and work on from a data point of view. And that's what we're going to talk about a little bit later in terms of data science. So let's make the assumption that we have something connected today, and we're moving data from that thing that's connected into the cloud. Well, what does that architecture look like? And really, without giving you a PhD in IoT architecture, just some of the highlights, there's components that make up an IoT environment. And you can see I've broken this into two separate sections here, data in motion and data at rest. Data in motion is meant to encapsulate all this transmission, accumulation, and aggregation of data from the physical device layer. And you can think of a physical layer could be a simple sensor like a thermostat. And all I'm doing is I'm checking on the temperature of an environment every 30 seconds in order to make decisions about how to maybe adjust for the comfort of the people in a room, or maybe adjust for an entire factory for energy management and savings. So that physical layer can be very, very simple to very, very complex in terms of very large arrays of computing power that provide this data. And then the second level is connectivity. So all of the networking and enablement to move that data from the physical device and into a computing environment. The third layer we just touched on, which is the edge, which gives us an ability to focus on very fast analysis of high volumes of data in real or near real-time environments. And then at level 4, this data is converted from being in transit or in motion to data at rest. And that's the next level of this IoT architecture. And this is the assumption of when you start getting into the cloud and you're going to perform different actions on that data and provide different services to your business community. So without going into all the details of how you do that, what you're going to do is start naming that data, tagging it, making it useful to the business, and then creating the applications that consume that data and provide business processing to your user community. And then the last layer is to collaborate around that data and be able to share insights and use those insights to make better business decisions and add value to your business environment. Right, so that was the Internet of Things very quickly. The next topic we're going to touch on is data science. Now, again, I think there's been a fair amount of hype in the market about data science and how valuable data scientists have become and the kind of entry-level salaries that folks can earn coming out of college. But I think there's also a lot of misconception about how new data science is. The term data scientist was really coined way back in 2008, so it's been around for over a decade. And companies realized that they had a need for data professionals who were skilled at organizing and analyzing very large amounts of data. And mostly that data at that point were audits, were logs of security or authorization into systems and other big data environments such as social media. Now, effective data scientists are able to identify the relevant questions that we need to ask of that data, collect the data from a multitude of different sources, organize the information, translate those results into solutions, and then communicate their findings through various tools and activities in a way that will positively affect business decisions for the whole organization. So data science is really the key to making all that data useful and being able to use it in the organization. And it's the art of wrangling very large volumes of data to predict future behaviors and then uncover patterns and infer meaning in that data and correlate it in new ways and draw meaning from what sometimes can appear to be chaos. So data science is a discipline. It's not a brand new discipline, but is an overlap of a lot of other things that have been around for a while, such as computer science has been around for over 60 years. There's a great mathematics foundation to it. And the kind of tools that data scientists use to do their jobs include things like data management tools for acquiring that data, storing it, processing it, profiling it, and then distributing it. And then data exploration tools where there's a term called mining, where you can dig down and find the nuggets of insight and value in large sets of data. They also end up modeling that data, which we'll touch on in a moment, with things like machine learning tools, and then clustering and summarizing the data for the business. Of course, there's also the aspect of data analysis to start looking at how do I predict behavior based on past. And they use mathematical models like regression and qualitative curves. And then the last thing is, how do they communicate, and tools to communicate the data in a simple way using reports, visualization, dashboards, etc. So all of those things make up the modern practice of data science. Jumping into machine learning. This is an extension, if you like, of data science, but it's a method of data analysis that automates analytical model building. So it's a branch of artificial intelligence, and it's based on the idea that systems can learn from data, can identify patterns, and can make decisions with minimal human intervention. So instead of that data scientist sitting and working with large data sets and doing all the things I mentioned, like exploring the data and collating and sorting it, we're actually going to have the machine, a computer, do that at very large scale. And we're going to automate a lot of that previously human endeavor using smart models. So data scientists can then build what are known as machine learning algorithms. It sounds similar to data science. It's a little bit different in that there's a foundation here for guiding the machine to learn based on these different algorithms that are available. And the outcomes, the models that data scientists build, let them loose on hugely powerful computers do all the heavy lifting. Now, these models or algorithms can be fairly simple. An example could be anomaly detection, where I've got a single data point that's flowing through the system continuously, and we'll go back to the temperature example. And we can say that we have a comfortable temperature range for humans of about 0 up to 60 degrees Celsius. But above that, humans are going to start dying pretty quickly, and below that, they're going to be very cold. So what you can do is tune the model to understand the range, and then to take actions once data is out of range. And that's called anomaly detection. So I've got spikes in that data that's coming through. And then there are an analog to that are slowly changing trends. So data values trend up or down over time. And those are algorithms that are fairly simple to code and to deploy. But then these machine learning algorithms can get very sophisticated, such as to predict and analyze and detect fraud on credit card usage. And I think most people would have heard that that's been around for quite a while. And large credit organizations have been using machine learning to predict fraud for a long time. Now there's a whole new branch of machine learning that companies like Microsoft are introducing, which are cognition models. And cognition models are algorithms that emulate and replicate human sensory data, so vision and sound and even smell. So there are new models that data scientists are building today that can detect breakage on a production line or faults on a product as it comes off of a line at very, very high speeds, using standard off-the-shelf camera technology, but with sophisticated hardware acceleration, and then these machine learning models running on the edge on a computer to provide instant alerts to the human operator in the mix. One thing to realize with machine learning, I think there's also been a lot of press or misconception that AI and machine learning is going to replace human activity, and I think that's as far from the truth as it can be. Is the whole idea that we're focused on is how to further enable and augment that human activity using automation and using computers. Ultimately, the benefactor, the person who's going to benefit the most from machine learning is that person doing a job where maybe there is so much data to analyze that they can't possibly do it within a reasonable time frame. And that's where you're going to use the machine. All right, so I think I bored you enough with the technical stuff, but let's do a quick level set, a midpoint summary here, and just agree on what we've talked around for the last 10 minutes. So IoT, the Internet of Things processing, provides us all the rich data that we need. And what we're going to use with that is have data science explore and gain new insights into that data, and then build and develop machine learning algorithms that are deployed to the edge and the cloud so that they continuously monitor, evaluate, and take action on that data. And that's meant to add value to many and various business processes and outcomes. So all of this is focused on how do I add value to the business that I'm doing today. Now, why should I even care? You might be asking yourself, because I certainly did a couple of years ago before I got very actively involved in this whole new world. And really, the simple answer is money. There's been a ton of research and over the last few years around IoT practitioners, and McKinsey reports that companies that have adopted IoT, and they define the leaders are those that are in about a 6% segment who are aggressively using the new technologies and are moving more and more processes into pilots and proofs of value and then into production. And what they're seeing is that people who are aggressively using the IoT environment are seeing cost and revenue gains of about 15% or more on their business. With those companies that aren't doing so much, they are dabbling, they've started some IoT things, maybe they're doing some labs or workshops, but they're lagging behind these leaders. They're seeing less than 5% in terms of any gains to their organization, which is better than zero. So if you haven't done anything at all, obviously you're not making any use out of this IoT and machine learning environment, you're not seeing any gains because you're not doing it, that's obvious. But for those that are doing it but just dabbling, they're still seeing gains, but 3 times less than the leaders. Now, the other thing that might not be 100% intuitive is that IoT leaders throw a lot more use cases at their IoT environments. So they're trying to anticipate questions that they can ask next year or the year after and prove out that if I can answer those questions using this modern and new processing capability, then I can anticipate a whole lot more profit based on the processes that are going to be accelerated, enhanced, and made more accurate. So these leaders are also learning a whole lot faster than folks who maybe are not doing IoT or doing it in a less capacity. So you'll see this is just another view of that data that I put up before, explaining what we define as leaders and laggards in the space. This is assuming that you are doing IoT already. And what I can encourage you to do is if you already started down this path and you started looking at IoT, it's the use case variety is going to make a big difference to your organization. The more IoT use cases deployed, the more your returns multiply. And McKinsey, again, has done a lot of research in this and has data to back it up. So what IoT leaders learn very quickly is how steep that learning curve is. And it's really essential to run as many pilots or proofs of value as you can to learn more. And they've discovered that the first 15 or so IoT use cases that you do typically have a modest payback. But the average payback rises quite dramatically until you've got approximately 30 side-by-side use cases achieved. And then IoT leaders anticipate that those IoT use cases will boost their gross profits by up to 13% over the next 3 years, 3 times as much as the laggards. And again, why would you do all of this? To stay in business. Make money, obviously, but you also want to stay in business. So this chart was research that was done at Yale, and Microsoft used it quite a lot to demonstrate this curve over the last 60 or 100 years is that companies very rapidly fall off of the S&P if they're not deploying modern technology. So you can see this curve is accelerating as well, so that companies are spending less and less time at the top of that chart, the top of their game, because the technology that they've depended on for a while becomes obsolete, and then they struggle to adapt to that and to move forward. So this new boom, this cloud servicing, is about 4 or 5 years old, and you can see that 75% of companies are are not even on the index today will be in the next few years, because they're taking advantage of all this new processing capability using the cloud and things like IoT and data science. Okay, so I hope just very briefly in a couple of slides I've convinced you this is something worthwhile to consider doing. Now, how would you do that? So I want to turn to some practical use cases. All of these are actual examples of things I've worked on with Hitachi over the last couple of years in these different segments. So if you're on the call today and you're in the manufacturing segment, let's talk a little bit about product quality monitoring. So I have a case study with a customer right now that is in the food processing environment, and they have a problem with the quality of the final product. The way that they've always assessed quality is a purely human endeavor in terms of the cognitive senses of picking the end product up, crumbling it between their fingers, in some cases smelling it, and definitely just looking at it and assessing, is this final product up to the standard, the quality standard that we expect at our company? And that assessment is based on many, many years of producing the same product. So the operators have, on average, spent 20 years on the line producing the food and assessing the quality. And they'll do a sample every 15 minutes or so. Now, as you can probably understand, that's not very scalable if you're going to build out and grow a big organization. And also, what it's not doing is taking the startup costs into effect. When you start a new product run, the first 15 or 20 minutes is wastage because you're only sampling every 15 minutes. So what we've been doing there is looking at a system, and I'll talk about this more at the end of the presentation today, whereby using machine vision, so cameras on the line, and various sensors that are set up to provide things like different temperatures at different points, the shape, the thickness, and various other factors around this particular foodstuff. Machine learning algorithms can actually be deployed to do real-time monitoring and optimization of that food product. So that's one area you can consider. Now, the machine itself can also be monitored for efficiency. So various sensors can be put on the machine if it hasn't been wired for operational technology already, to get things like the speed of the motor, how much draw is the motor taking at any one time, what kind of vibration is there on this machine, what kind of standard do we set in terms of the uptime on the machine, how long it runs before it needs maintenance. Then the maintenance itself, can we predict when various components might fail, and then get ahead of the maintenance and replacing those components? So these are all use cases that are very much active today and are being worked on by our company. One that maybe is not all that intuitive for IoT is smart job scheduling. And what this involves is being able to integrate back into the ERP system and the PLM system for specific products and components that have been produced, and then to check on the load on the various lines themselves, and to build an algorithm that essentially, in this case, somewhat does replace the human endeavor for scheduling loads and scheduling jobs. But what it'll do then is automate the setup for a particular line and predict the best and optimal chart for job scheduling over time. Now, turning to field services, where our company, Hitachi Solutions, is particularly strong. If you're in a field services organization, predictive work scheduling is something that I've been asked to get involved in a lot. And it's often based on the predictive maintenance of assets. So an example that I was working with recently is a large landscaping company. And they have thousands of crews across North America who go out to landscaping jobs, small or large, every single day. And what they find is they've got this job board that each crew at their local level will maintain. And you've got a lot of complexity, of course, with folks who might not show up for work, especially if you've got a crew leader who doesn't show up for work. He's the person or she's the person that's going to be driving the truck that day, you've got to do a lot of last second adjustment. But what we demonstrated is that we could actually ingest all of this data over a year for all the jobs that have been contracted and all the subcomponents of a job, like mowing the lawn, trimming bushes, putting down fertilizer, pruning trees. They can all be broken out into fairly simple building blocks of expectation of how long they should take. And then the algorithm basically tallies up all of the hours that are going to be spent in any one particular day, week, hour, month, and the whole year, and then as smartly assigns all of those jobs to crews based on a crew mix, and then assigns them daily to do that work to maximize the amount of effort that they can produce in a day. Now, associated and very much aligned with that is smart routing. Now I've got a crew out that maybe, and this another use case I'll talk about later, is I want to replenish the oil at a Jiffy Lube. Well, in the old days, what would happen is that the owner of the Jiffy Lube or the mechanic would go and kick the 5,000-gallon oil drum and listen to how full it is. And if it was running out of oil, they'd make a call to their supplier, and somebody would then schedule an oil delivery. Well, by simply putting a sensor on that tank for how empty it is, we can now automate that data to be sent to the supplier. And then based on the actual tanks that need replenishment, the algorithm figures out for the fleet the smartest route, the optimal route to actually go and fill up those tanks. Another thing I'd like to talk about there is asset tracking. So if you have an organization that takes high value assets out into the field and you find that now and again they get lost, they get left behind, we can actually have an algorithm where you can put a simple RFID sensor or Bluetooth sensor onto those assets, and you can track them in real time with GPS and Wi-Fi location services, and then make sure that you leave a job site with everything that you took on. Now, the last sector to talk about quickly is energy, because this is very, very interesting to me personally, so why I put it in there. I just got back from Toronto last week, where we were working with a very large property management company, and the use case here is heating systems. And this can apply also to, obviously, cooling systems like HVAC. But the boilers in a cold climate are the things that you rely on to keep your apartment heat. Keep it comfortable for the tenants. So what we've been working on is, can we get data from those heating environments, the thermostats, the boilers themselves, the water flow, and the different subcomponents, the pumps, etc., and then put them into a system which optimizes the turn on and turn off of those systems so that we can maximize energy gains and actually stop paying so much for energy. And what we've actually done here is incorporate weather data. So we actually have a weather forecasting system that's very accurate that we associate with that data. And then we can start predicting, hey, the temperature in Toronto is going to increase steadily over the next 10 days, and there'll be a temperature swing of 3 to 5 degrees. So midpoint, can we turn the boilers off to the parking areas, for instance? And then what kind of energy savings can we see from that? And the algorithms that are built out can do that prediction and then also do the real-time activity of turning the boiler on and off without any human intervention at all. Now, the second example is also fairly technical but interesting, and it's called gas lift optimization. In the oil drilling world, at the wellhead, certain of the oil fields, especially those that use fracking, use what's known as gas lift to get the oil from 10 or 20,000 feet below the surface of the earth to start lifting up of the pipe that's been drilled and inserted down. And so the oil company will then, or the operator will inject gas into that column and thereby lift the liquid, lift the oil up. And there's a science behind this. There's a whole lot of data behind this that can be accumulated. And the algorithm that we've built actually predicts how much gas needs to be injected at any one point all the way down that column to get the maximum lift and reduce the amount of energy that's required, and then obviously maximize the flow rate, which is again associated to the value, to the actual revenue. If oil's not flowing from your well, you're getting $0. If you can maximize the oil flow from that well and reduce the costs, then you're maximizing the amount of money that you make and your profits. So all of this, again, all this technical stuff is associated back to driving value back through your business. The last quick example I want to talk about there is natural gas quality management. There's a big industry that is associated with taking raw methane or methane produced by various factors. It could be animal waste or landfill waste, or just natural method that comes from the earth and under the sea, and taking that and scrubbing it and cleaning it and adding the components that make up a consistent and standard natural gas that can be injected back into the utility pipeline and then used to power and heat your home or for cooking, etc. So that energy sector. Now, the quality of that gas is very important to the utility company, because if the gas is poor quality, i.e. if there's too much water vapor in the gas, then it can cause corrosion issues on the pipeline, it can cause valve freeze, it can cause a whole lot of negative impacts downstream. So the algorithm that we're looking at is to actually take a gas sample every few minutes, break it down into its components using sensors, and then accumulate that data into a model which optimizes the quality at any one time. What that will do is reduce the amount of negative impact and any shutdowns, because the negative impact to the producer is that the utility company, on determining that the gas quality is suboptimal, will often just shut off the valve from that producer. And then it could take 3 days or 4 days or even a week for the utility company to send somebody else to do an inspection to certify that the gas is back at standard and turn the valve on. So again, you're down for that length of time, you're not producing any money. So the negative impact to your cash flow is really severe at that point. So the machine learning and the IoT environment here is designed to maximize the quality of gas at all time without human intervention, and thereby preventing shutdowns. So I hope that those few business case examples are practical for you, that you can see all of the technicality and science behind this has a point, and that it's always designed to optimize a process and to gain maximum value for a company. So let's talk about how we do that as a company. So we have a philosophy at Hitachi, which is crawl, walk, run. So the other cliche is don't boil the ocean. Don't throw everything at the system and trying to make something out of nothing. We try and evaluate and get very focused on a specific example, or we call them use cases. So the first thing that we'll do is just a discovery call, and to me, I'm calling it the 111 process. So the initial discovery call, talking about, hey, I've got this business outcome that I'd like to drive. There's a suspicion that I could use the technology available out in the world today to do this more accurately, to drive optimization. I can do it at larger scale and thereby drive more value out of this process. And I want to talk about it. So we encourage just to have an initial discovery call, and it takes about an hour for us to kind of listen and diagnose and see if there is a applicability of this technology to that problem. Then the second one is 1 day. It's based on that to set up a use case definition workshop where we work with subject matter experts on that particular process or that outcome, and we do a deep dive and document everything to do with that process and the business outcomes that are desired. And then the next one is 1 month. Do a proof of value project, which is just a lab where we implement as much as we can historical data. If we need to capture data, to do that as simply as possible. We can even do data simulation without physically having to put any sensors on a line or a piece of equipment. But what we try and do is prove that using IoT, machine learning, data science, that we can come up with a model that's going to do any of those examples, predict something, or optimize a process, to monitor, to provide alerting and reactive feedback. And we do that very quickly, and we aim at doing that within 30 days. And then if we can see the value and we can prove it, then we refine that model so that we can scale it out and take it out to production and deploy it in your organization. And then iterate, go back through that and look for the next use case and the next use case. Once you have this architecture platform in place, it doesn't cost that much more to throw new projects and new use cases and labs at the architecture. It's that initial startup that takes a while, but once you've got it running, you can iterate and build new use cases and new proofs of value on that very, very quickly. So we call it a proof of value. Our process looks like this, where we'll look at the current state, do the discovery, and then document all of that through a use case definition. And then take as much data as we can from either sensors that you already have or data that's been generated within devices that provide real-time data. And then also take as much historic data as we can, if you have it, or we can simulate data. And then start building the machine learning algorithms to provide the predictive view. In this case, it's a predictive maintenance proof of value. And then we'll tag that data and we'll start enhancing the process and looking at how we provide an outcome using that algorithm and whether or not it's going to be on the edge and what kind of processing power we need, and start getting smart about the infrastructure, and then optimize the learning so that the next part is really a training exercise for the person who either manages that process or runs that specific machine or ultimately is in charge of the data and the outcomes, and then move that over to them and finish off the case study by looking at an impact study. So is there revenue to be gained? Are there costs to be saved? What kind of operational efficiencies can we expect or achieve through this? And then very importantly, what are the impacts on CapEx or OpEx budgets over the next year or 2 years? And so we start getting granular on what does that cloud service look like. Microsoft provides, at this point, thousands of different services up in the cloud. Which ones are most pertinent to this process? What do we anticipate that they'll cost? And then provide a value justification back to the executives at the company so they can make a decision about whether or not they want to deploy this IoT architecture. I hope that's made sense for you to this point. The next slide is a little bit technical, and this is the architecture that Hitachi Solutions has developed as intellectual property. All of this architecture, I'm not going to go through it exhaustively because it'll probably just bore everyone on the call, but suffice to say that it's built on the Microsoft Azure cloud environment. And all the services that are available on the Microsoft Azure cloud platform are available to this IoT architecture. So we talked about the data science activities of data accumulation and tagging and storage and analysis and integrating that data to the enterprise, and then be able to communicate and visualize that data and get it out to the organization. We talked about a little bit about artificial intelligence and machine learning, and creating a platform for data science and all that data analysis. And that's all incorporated into this architecture. So it's a very quick deployment into the Azure tenant. It takes about an hour to get everything set up. And then it takes about a half day, and we can start getting data flowing all the way through from a device into a dashboard and actually start looking at data flowing through the system. Now, the big differentiator that we at Hitachi have deployed is in this action workflow box, where we've integrated this architecture into the Microsoft Dynamics 365 connected field services environment. So not only can we do all of the data science and the machine learning and set that up for monitoring, but we can trigger an event based on some alert that comes through this evaluation engine. And the example that I had was a temperature that is too high. That can automate an event into Dynamics 365 and actually create a case, a ticket or a case. It can create a bill of materials. It can activate a technician and assign a resource to a problem. So all of that can be automated, and a person or a team sent out to site to fix a problem that you didn't even know was happening. So that's why one of the ways we refer to this environment is a predictive services hub or environment. And that's the thing that we bring to bear on this whole problem space. So the last thing I promised you was some real life examples and how we actually changed the business for a handful of customers. So the first example I have is in this field services arena, and I talked about before the monitoring tank levels on oil tanks. And that wasn't just a hypothetical, we've actually done this in Canada. And what the outcomes were was to improve the service efficiency for repair bays, so about 4,000 or 5,000 now that are serviced by this model. Previously, there was no remote monitoring at all of the tank levels, and they're just replenished by schedule. So trucks would get on the road every single day, drive a route, go over to the tank, kick the tank, figure out if it needed oil, top it up, figure out how much that it would actually consumed, and then send a note to the back office and the customer would get an invoice. So what we did is we helped this company put simple devices to actively monitor the tank levels on the oil tanks. And then if they were depleted by a certain percentage, to automatically generate that work order and flow straight into the backend system. And then the second outcome for them was route optimization. So instead of going around on a schedule, was actually to build a smart route for any one particular truck on any particular day, so that you could load just the amount of oil on the truck that was necessary to fill up those tanks on the route. So this customer in this case have completely changed their business model using this technology, and it wasn't a huge financial impact on their business outside of the actual equipment that was deployed, but the algorithms and the architecture that was built for them was actually very surprisingly reasonable from a cost perspective. Now, associated with that, very similar to that, but is monitoring and prediction on tanks that are completely remote. So they're not in this urban environment in a repair bay, but they're out in the middle of nowhere. And this is for the fracking companies. And but very simple. Trucks will travel from tank to tank. They don't know if they need to be serviced or not. And in this case, it's actually collecting the fluid from a tank that's filling. So you can imagine that it's filling up with water or oil at this point. So at each tank they would connect to, they would do a quick with an app, figure out the fluid level, the flow rate, pump status on that tank. They record the measurements on a spreadsheet, so it's all completely manual, and then feed that into the backend system when they got back to the base. Now, if the tank requires anything, then a new truck would be dispatched, for instance, for chemicals or for sand, and then they would go and fill that up. So very manual and suboptimal process. So again, the solution here was to add sensors to the tanks and to the pumps, so we could capture all of that data through the IoT environment. And the goal was to minimize the number of trips that trucks have to take. And the business value there is to save a whole lot of fuel and, of course, time. Then we can also provide the client information in advance in terms of which environments need servicing. So you can get some predictive maintenance on this as well, is that maybe a pump seal is struggling and we're monitoring flow rate and we can see it slowly trending down over time. There's most likely a suction problem, and we can scramble a technician to take the parts out there, and that is completely all automated. So you're going to reduce a whole lot of cost, especially if your pump fails, then of course you're not producing anything, and that's disastrous to the company. So these are the kind of visualizations that can be very quickly built on that backend Hitachi environment that I talked about. And we use a Microsoft visualization component, use Power BI to interpret all of the data and then provide visualizations like maps using GPS coordinates, charts, tables, and all of this can be done in pretty much real time. So we can have sub-second refreshes on these dashboards flowing through Power BI. Nearly there. The second last example I wanted to give you was worker safety. We've worked long and hard, it must be 18 months at this point, to develop a very robust environment for worker safety using wearable technology and then our IoT service hub to interpret all of the data that's coming from equipment and from the worker themselves. So in this use case, we're looking at miners and we're connecting them using a wearable that literally a watch. And that smartwatch has an application on it that submits the heart rate, the location, the battery life, and other information like accelerometer data, how fast they're moving. So we know if they're on a vehicle or not. We can also tell if they've fallen down based on the accelerometer data. And that watch communicates every 10 seconds, it'll send the heart rate and the GPS location through the system. Now, all of that data is then visualized to a map for the health and safety operators on the mine, so they, at any one point, know exactly where all of their workers are and the health of that worker. Now, there are extensions to this application that we're building as well, so we can do things like very simply take the number of steps that they've taken in a day, the temperature conditions that they work under, and we started building out things like fatigue prediction. So we can look at an individual worker and we can figure out whether or not they are getting fatigued, and then start predicting over time based on their actual biometric data when they're going to get fatigued. So that allows us then to schedule a health check for them, to maybe look at diet and hydration needs for that particular worker. And then, of course, very importantly, is give them time off to recover. Some of these workers work in 50 degrees Celsius temperatures for weeks on end. So all of this is going to promote for the company the ability to attract new, younger workers, because it's all technology based, into what is pretty much a dying breed. The miners, are getting older and older, and then also provide them, emergency prediction and monitoring and give them safety. The other thing that we can do, and we are doing, is hooking up other sensors, environmental sensors like air safety, to look at gas levels, hydrogen sulfide and CO2 and carbon monoxide and that kind of thing. And then also particulate data. So how toxic is the environment that they're working in? Are they actually using their breather technology and their tanks when necessary? And we have vision systems that can actually detect when a miner has their hard hat on or not, and send them an alert that they're entering an environment that they have to be wearing the hard hat. It's just a whole host of things associated with the actual workers' safety and health. And the last one I want to talk about a little bit is this quality control for manufacturing that I had touched on before. And this is to really improve and enhance the existing quality control process, which is mostly manual. And the goal is to reduce wastage. So for this particular client, the current annual wastage is tens of millions of dollars. And what they desire to do here is to automate as much as they can and innovate, remain a leader, and then use all of this IoT data and analysis to prevent that wastage as much as possibly can be accomplished. So this is a very, very difficult problem to solve. As I said right at the start, some of the technology is in its infancy, but we are equipping the line in this particular example with laser, temperature. All of this is non-intrusive to the food line, by the way. So laser, temperature controls and monitoring. We're using a lot of cameras to look at the actual condition and quality of the food that's coming off of the line. We're connecting that to an edge controller, which is going to manage all of this in real time. So large computing capacity. And then all of that anomaly data will be fed up to the cloud with machine learning algorithms, which will recognize when food is out of tolerance, out of specification, and send an immediate real-time alert back to the operator. The other thing that can be done is that we can actually use actuators on the machine to get a tight control loop, so that once something has gone out of tolerance by a certain percentage, the system, this system will actually control the machine in a feedback loop. So that's the last example I had for everybody on the phone. I hope this has all made sense for you. Basically going to wrap it up at this point and just tell you something that you probably already know, that these environments, as young as they are rapidly becoming mainstream tools. So we're seeing more and more adoption and interest every single day. I'm not exaggerating when I say we get a new discovery call or use case every day here at Hitachi Systems. Now, one of the tricks for you on the phone is select a technology platform that's going to minimize your implementation time and costs on startup. So our philosophy of crawl, walk, run, start looking at a 1 hour, 1 day, 1 month type of approach, and then move very quickly to proving those use cases in or out. So you start with a minimum viable solution for one use case, try and show value on that within 30 days if you can, then iterate quickly around that, add value to that process every 30 days and get it into production as fast as you can. Then once you have that model, you've got the architecture on the platform, all the underpinnings, then add use cases onto that as quickly as you can, identify them, and maximize the time to value and your ROI. With that, I am done, and I hope I provided some value to the audience today, and we'll open up the floor for any questions.
Thank you so much, Richard, and thank you so much for sharing all that wonderful information today. So we'll just wait a moment to see if we have any last questions come in from the audience. And again, if you folks have questions, please feel free to type them into the questions box to your right. And as we wait, I just want to again confirm to the audience today that we will be sharing today's webinar recording with all attendees. So you will be receiving an email shortly to view the recording. And if you happen to think of questions later or after viewing the webinar, again, you can feel free to reply to that email and our team would certainly be happy to help. So we'll just give it just one more moment. Let's see if we have any questions. Well, it doesn't look like we have any questions at this time, but again, if you think of questions later, please feel free to reach out to us. We're always happy to help. And we want to thank you all so much for your time today and for joining us. And we hope you all have a great day. Take care.
Thank you, Ashley. Bye now.
Thank you. Bye.